and good morning, everyone, to Monday morning of IndoCrypt. For those of you who are in India, it's a late morning. For me in Europe, it's an early morning. So we're starting off with the session on implementing elliptic curve cryptography. And it's my pleasure to announce the first speaker, Abranil Datta. And Abranil, could you please unmute and share screen? And everybody else, could you please mute yourselves? And if there's any questions, please post them to the Zoom chat.
Hello. Hello, everyone. Hello.
You should be able. Good morning. Hello. You should be able to share your screen.
Okay. Yeah. Okay. So my talk is on extending the signed non-zero bit and sign aligned column methods to general basis for use in cryptography. So my name is Abranil Datta, and the other two writers of this paper is Aaron Hutchinson and Koray Karabina. I'm from Florida Atlantic University. Aaron is from University of Waterloo, and Professor Koray is from National Research Council, Canada. Yeah, so I have divided this paper into four sections: the introduction, theoretical results, and the cryptographic applications, and some concluding remarks for future works. So first of all, these are the basic things, like we know the Weierstrass form of the elliptic curve, and we know they form groups, and the point inversion is very cheap. That's why we prefer to go for elliptic curves. So, and then we know that for the elliptic curve scalar multiplication, we can either go for a one-dimensional, or we can switch to multidimensional as well, where we calculate summation of AI, PI, where AIs are the given scalar, PI is the given points. And some works was, so for the cryptography, because in this multidimensional scalar multiplication algorithm, first was introduced, I guess, from Strauss algorithm, but since in the algorithm 0 appears in the binary representation, so while performing a double and add, in some steps we skip addition, so that's why there is an irregularity. So we go for a scalar recoding. So whichever scalar is given, we recode them into non-zero representations, and then so that way we make the algorithm regular. And previously the scalar recoding algorithm was done by for binary case, it was done by Hedabu, Pinel, and Benetu, and Joy and Tunstall did it for k equals 2 to the power m base. So what we did, we generalized it for any k, and for sign alignment column, we also generalize this from binary to any positive integer. And we give two algorithms, one recode, one align. What recode does is it records a given k-array representation of a scalar into a non-zero representation. That means we get rid of all the zeros and we replace them with negative and positive digits or numbers. And for align algorithm, for a given sequence of signs, we can align them. Means we recode a scalar in such a way so that it agrees the sign sequence. That means if the sign is positive, then the sign of the digit will be positive, either positive or zero. If it is negative, then either zero or negative. So, and in our theoretical results, we call scalars in a binary representation. If these kinds of sequence comes like 000J or 0001 in case of binary, so we replace them with this function, That means these functions, what it does is it gets rid of all the zeros and all the zeros in a key array representation. So quickly, I will give you an example. So this example says that if this is the given binary, this is a ternary representation, or in this ternary representation, we replace, we call them bad strings because zeros appear, okay, in this sequence. So we get rid of these zeros by replacing them by, suppose for 0, 2, I replace it with 1 and -1. For 0, 1, I replace it with 1 and -2, and these are defined by the functions. These are following the function definition. And after we recode them, the value remains unchanged. So, but in this case, what happens is, like, since the bad strings or these strings, these zeros, ones, and 002s, they may have different length, so it's still not regular. So in that case, we give a table which we call a lookup table. So what we do is, like, what our regular recode algorithm does is, we trace the scalar from left to right, and we replace them with the suppose for ai -1, we replace that digit with the from the lookup table from that particular position, ai and ai -1. So for example, if this is given, this is the sequence. So for our algorithm, what it does is, for the first 0, we replace it by 1, and from the next one, suppose 0 and 1. So whatever it appears in the table M01, we replace it by that entry. So, and then for our sign alignment algorithms, if a sign, a sequence of sign is given, which is represented by 1 and -1. So if it is given, so we can recode a scalar according to the sign sequence. So what we do is, we follow this table. So this is the sign sequence. It can be either 1 or -1. And this is the scalar. These are the scalars 0, 1, 2 to k -1. So for example, suppose we are given this sign sequence 1, -1, -1, and so on, and we are given this scalar to be recoded. So what it does is, like, in this case, it follows the table which is given in the previous slide. Like, sign sequence is 1, this is 0. So what we do is we go back to the table. So when it is sign sequence is 1 and entry is 0, we do nothing. So that's why it remains unchanged. And the next step, when it is -1 and 2, we again go back to the table. -1, yeah, -1 and 2. So what we do is, we replace that replace the entry by the entry of the table, like whatever the rule is given in the table. So the rule is, like, we do -k -1, which is -1, and we add 1 to the next one, which gives it 2. So this way we recode the scalar. So at the end of the day, you can see the sign. So whatever the outcome is, it agrees the sign. That means if it is positive, it is either 0 or positive. If it is negative, it follows the negative. So that's why that's how we recode the scalars in this way. So what it does is, actually, so this is our align algorithm. So there are many if conditional statements. So we replace them by this function, and we get a regular structure of the algorithm. So
could you conclude? We're approaching the end of. Okay, thank you.
Oh, so for concluding remarks, like, we use this recode and sign alignment algorithm to give a scalar multiplication algorithm. So yeah, and in that scalar multiplication algorithm, depending on that, we give a cost of our algorithm, which is like storage cost and computation cost in terms of number of points in the pre-computation stage, and number of k multiplication and addition we are performing. And we also use, like, another method, like split and com method, where we further, like, divide a scalar into more subscalars, and depending on that, we give further implementation. So in conclusion, like I want to say that this like applying this recode and scalar multiplication, what we have is for a fixed k, for fixed d, like the scalar with the number of subscalars. For fixed d, we have a better result for k equals 3 rather than k equals 2. So yeah, that's it.
Okay, thank you very much. I think we have time for 1 or 2 short questions. Pratyay, do we have any questions?
I don't see any. Actually, I can ask a question I have in mind. Do you want to talk a little bit about the cryptographic applications, like immediately what it impacts?
Oh, what it impacts is for suppose for Diffie-Hellman, we in first round and second round we do scalar multiplications. So in that case, we for a given scalar we divide that scalar into subscalars like 3, 4, 5. Okay, and then we perform like Strauss type of algorithms like double and add, or in this case k multiplication and add. So that's how the number of iterations gets smaller when you multiply, when you perform like multidimensional scalar multiplications. And for that means since we want to get rid of zeros, and when you align the algorithm, like so what it happens, like you first recode the top subscalar, you put it in matrix. Okay, you first record the top scalar into all non-zero representations, and then you align the rest of the subscalars representation. So in that way, in a line, in a column, either you have all negatives or you have all positives. So we know that so once you store in your pre-computation stage all of your points, there you only have to store positive points, because negation comes for free. Okay, so that's why our storage becomes less, our number of iterations becomes less.
Sorry.
Yeah.
Okay, thank you.
Thank you again. I don't see any more questions in the chat, but please continue writing questions there. Then if we have time at the end of the session, we can still ask questions about all of the talks if there's time. All right, so thank you again for the talk. Maybe you can stop screen sharing and then we can proceed with the next talk. And it is my pleasure to announce Melissa Azouawi, who will be giving the next talk. Melissa, maybe you can start screen sharing and unmuting yourself, and then please start. That looks like it works.
Hello, can you hear me?
We can hear you very well, thank you. Yeah.
Yeah, I will start the screen sharing. Can you see my slides properly?
We can see the slides, but they're not maximized. So as you like. But we can see them.
I guess I can change it. Oh. How about now?
And now looks good. Yeah, now perfect. Yeah.
Okay, thank you. So so thank you very much for the introduction. So my name is Melissa Azouawi, and I'm a PhD candidate at NXP Semiconductors, Germany, and UCL Belgium. And in this short presentation, I will be describing our work titled on the worst case side channel security of ECC point randomization in embedded devices. So we already know that single trace DPA attacks can be applied on the main ECC operation, which is the elliptic curve scalar multiplication, or ECSM for short here, and this with the knowledge of the input point here denoted P. And so in order to hinder these attacks, we can use the point randomization countermeasure, which randomizes the input P into a point P prime by using a different elliptic curve representation and a random secret value here denoted lambda. So in this work, we present the first systematic analysis of the point randomization countermeasure against worst case side channel attackers. So the main operation in the point randomization is a field multiplication of the secret lambda by a point coordinate. So in order to break the point randomization and recover the randomized point, or equivalently lambda, the attacker needs to recover lambda from the leakage of the field multiplication. So in the following, we will take as a simple running example a multi-precision schoolbook multiplication, and which is then followed by an independent modular reduction. And this was the option we chose to implement the field multiplication. So here we show the general structure of the example field multiplication. So it consists of multiple single precision multiplications. And then all the results of these single precision multiplications are accumulated in this part. And then there's a final reduction that is performed based on the field. So from this architecture of a field multiplication, we can identify different attacks that exploit different amounts of information, and this for a varying degree of simplicity. So first we have horizontal divide and conquer attacks. And as the name suggests, they just attack each word or each register of lambda independently. And then we have another option which exploits even more information, which is to apply belief propagation or soft analytical side channel attack, which was introduced by Vera Charvion et al. At AsiaCrypt 2014, and this on the full field multiplication. So regarding the tools we use in the paper, so first we use, when we need more quantitative analysis, we use the concrete attacks that are described in the paper and also the corresponding security graphs. And when a more qualitative or comparative analysis is required, we use the recently introduced local random probing model, so LRPM for short, which was introduced by Go et al. And basically what the LRPM does is that it's an efficient tool to provide an upper bound on the information that can be extracted on a secret after an attack, so whether it is a belief propagation based or a horizontal attack. And this is done in a fraction of the time it takes to perform any attack. So some of the main questions we answer in this paper are, first, do time-consuming belief propagation-based attacks provide a significant gain, and specifically in this case of point randomization, and this in comparison to divide and conquer attacks, which can be easily enhanced with enumeration and also possibly at a lower time complexity than belief propagation. And to answer this question, we use the LRPM and compare both of the attacks on the field multiplication. The second question relates to how much noise, how much side channel noise we need to protect point randomization against nearly worst case adversaries. And for this, we perform simulated attacks and provide also the security graphs. The third question is how much security can we expect in practice from point randomization on common embedded devices? And to answer this question, we performed concrete attacks on assembly implementations of the point randomization. And finally, the last question is, can we use some shortcuts to lower bound the security of, for example, more difficult to analyze targets? And for this purpose, we make use of the efficiency of the LRPM, and this after showing that it does approach the results that we get from real attacks. So to conclude this short presentation, I would like to go over the main conclusions from the paper. So first, in this specific case of point randomization, the example we chose, we show that belief propagation-based attacks achieve similar results to divide and conquer attacks, and this for the high noise cases, which are the most interesting ones, and we explain in the papers the reasons behind this. Then we show the different, through the different kinds of analysis that we perform, so both simulated, real attacks, and also model-based, that point randomization can be implemented securely on small devices, which are typically referred to as insecure and also in software, but only if adequate optimization and also considerations for side channel attacks are taken into account. We also show that the LRPM can be quite can be used quite accurately and very efficiently to bound the security of the evaluated implementations, and thus can be used to speed up evaluations of challenging targets, for instance, on 32-bit platforms. I would also like to mention some of the additional contributions that are detailed in the paper. So in practice, we first analyzed belief propagation applied to the point randomization, and we compared different ways to construct the factor graph of the implementation to find the optimal one. We also extended the local random probing models to operations with multiple outputs. And then additionally, we also compared different types of coordinate systems, so both homogeneous and Jacobian, but this with respect to the security of the point randomization countermeasure. So as future work, so we took the example of the schoolbook multiplication, and we considered 2 different assembly implementations. But we can also consider different multiplication or modular multiplication algorithms, such as Karatsuba or Montgomery modular multiplication, which might change the conclusion which might change the result in the first conclusion. And also, I would like to mention that these belief propagation attacks are quite a recent topic, and it is worth investigating them in order to speed up these very worst-case side channel evaluations. So thank you very much for your attention, and if you have any questions, I'll be happy to answer them.
Well, thank you very much for this very nice talk. Are there any questions? I do see any.
I don't see any.
I could ask a very high-level question. Do you think there's any role for machine learning algorithms for doing side channel attacks? Since you mentioned other kind of attacks.
So surely there is a use for them, but in this specific case and the specific case of elliptic curve crypto, since if we want to approach the worst case security level of these implementations, and usually these implementations have so many targets and so many intermediates that we can use, which can be very easily exploited with like classical horizontal analysis and using even these divide and conquer approaches. So I don't see it as a way to exploit completely this, I don't know, 10,000 intermediates at once, because that would probably be too much for deep learning algorithm, and even for just basic multivariate analysis where you have to estimate the parameters. So I would say it is quite useful in this particular case for ECC to use it for to estimate the side channel leakage model. So if we follow a divide and conquer approach and attack each intermediate independently, then we can basically find the leakage model for each intermediate using deep learning, and then follow up with these very simple divide and conquer that are very fast, and yeah.
Okay, thanks.
All right, thank you very much. I think in the interest of time, because we're 5 minutes behind schedule, we should probably postpone all further questions to the Zulip chat. So please keep discussing there, please keep asking questions. And then, well, Melissa, thank you again. And then we will continue with the last talk of this session, which will be given by Mojtaba Bishinyasa. Mojtaba, could you start sharing your screen, please? And then please go ahead.
Hello, thanks for introduction. Just I share my screen. Can you see my screen?
Yes, that looks like it's
Okay.
starting. I can't see the slide. Yeah, now it's all there. Perfect. Please go ahead.
Thank you. Okay. In this actually presentation, we propose different FPGA-based implementation of the elliptic curve cryptography over curve 448. This is a work with, my name is Mojtaba Bishinyasa, with Dr. Reza Zardarash and Mehran Mozaffari Kermani. Okay, The curve 448 is actually standardized recently by NIST in 2019, and can offer a high security level after curve 448, which is targeting our previous work. This curve can be known as a suitable choice for a hybrid crypto system with some post-quantum scheme. Although this curve is designed about 5 years ago, but I was designed 5 years ago, but there are only few hardware implementation of this curve. Therefore, we need some more exploration of this curve from different optimization perspective. In this work, we target 3 different optimizations: lightweight architecture for IoT devices and area constraint applications, high performance architecture for time constraint applications, between area time to some specific applications. All of our designs are variable base point and are extended by side channel countermeasures. We use the friendly property of the curve 448 based on the special shape of this curve, and we use the Montgomery ladder for hardware implementation based on the projective coordinate. We design different scheduling for each of our design to increase the efficiency of the design. We also consider different side channel protection. Constant time, all of our design are constant time and secret independent implementation to avoid timing attack and SPA attack. We also implement the point randomization and S-score blending in our design. The hardware, the top level architecture for all this design is shown in this slide. The design one is our lightweight architecture using only one DSP. All computation in this design can be performed sequentially to minimize the required hardware resources. The design two shows our efficient area time efficient design using a fully pipeline multiplier, which can optimize our design. And our design 3 is the high performance design using a 5-level Karatsev multiplication. As I said, our design, lightweight design use only one DSP block, and our area time efficient architecture use the fast Karatsev multiplication. And we use different techniques such as the optimization techniques, such as the refined Karatsev identity and Python architecture. And as you see, our design can perform the throughput of our design is high. It can produce 164 by 64 multiplication per cycle and perform the 448 by 448 multiplication in only 15 cycles using the refined Karatsev techniques. I can show the performance of different architecture in this paper. As you see, our high performance design needs only 15 cycles, as I said, for multiplication, which can reduce considerably the total cycles for point multiplication over this curve. We reported a comparison between our results and different results over curve 448, and some implementation for the security level above 128-bit security. As you see, our lightweight design needs only few resources compared to previous work at the cost of increasing the required cycles. Our efficient design needs almost the same actually cycles with actually compared to previous work, with actually fewer resources, while in the high performance design actually can increase the throughput and at the cost of increasing the required cycles. For more actually, for better comparison, we visualize it. Here, as you see, our high performance design reduce the required cycle at the cost of the hardware resources, increasing the hardware resources compared to previous work, and our actually lightweight design needs only few resources in our implementation. The actual red points here shows our unprotected design. The blue actually shows the protected design using the scalar blending and point randomization, while the black point actually here shows the high protected design using the point re-randomization. The result actually shows that our design one can save 96% of resources compared to previous work with the competitive performance. Our design, our efficient design actually can improve almost 48% efficiency compared to best previous work with occupying 52% fewer resources, and our high performance design can improve actually efficiency almost 40% compared to previous work by increasing almost 12% throughput. And to conclude, we in this work we investigate 3 different hardware implementation for the curve 448, targeting area constraint application, time constraint application, and a trade-off between required area and actually utilized area and required actually cycles. We actually, all of our design has been implemented in the one of the Xilinx FPGA and extended by sidechain countermeasures. We can actually provide different performance level based on actually our application using the curve 448. Thank you.
Thank you very much. I think we may have time for one quick question, and then we would have another 5-minute break before the next session. I don't know if there's any quick question.
I can ask a quick question, like kind of high level. So you mentioned like using it for post-quantum hybrid schemes. So is it like for specific, like this should be used for the classical one? And is there a specific post-quantum class where it will be useful, like isogeny or something?
Actually, although we need actually the post-quantum scheme based on actually Shor algorithm, we have to actually use the elliptic curve cryptography in our design, at least until actually the post-quantum actually standardized will be applied completely. So the curve 448 can offer actually almost 220 actually 4-bit security, and can be actually combined with some post-quantum schemes such as the SIG actually P434 scheme to provide actually almost the same security level in both classical actually quantum security and post-quantum security, classical security and quantum security level. And we can actually use it such as, for example, in the signature design, it's really used to use, for example, in the ED448, this design can be used.
I see. Okay, got it. Yeah. Thanks.
Thank you.
Okay. Then I think in the interest of time, so that we have a 3-minute break before the next session, I think we should put all other questions into the Zulip chat. So please continue there to ask questions. So I would like to thank all speakers of this session again for their very nice presentations. And then we'll see everybody back here in 3 minutes for the next session.
Thank you.
Thank you.